This is the second half of vector day 2. So they ask us to graph this point, and in IB what we typically do, and we may have talked about this a little bit in SL, but I don't think we have yet in HL. No, we did, but whatever. Okay, so in this one, this is the x-axis, the y-axis, and then z we kind of think of as coming up off the page. So if we're going to graph this point, we're going to use a rectangular prism, and I've gone 4 units in the x, 2 units in the y, and so I'm going to turn this into a little parallelogram down here. And then I need to come up 3 units, 1, 2, 3 units in the z. So I have to do that same thing from each of these corners. Okay, and so this point right here, I've gone 4 units in the x, 2 units in the y, and 3 units in the z direction, and that's the point 4, 2, -3. So if I ask you to draw a point in 3 dimensions and you don't show me this rectangular prism, you won't get full credit. So there's that. I'm sorry. I'm feeling a little savage right now. Okay, if I say I'm at a corner of a box and I want to get to this other corner, see if that makes sense. If this is A and this is B, then notice that going across the bottom of the box, this is going to be, that little piece is going to be the square root of A squared plus B squared is going to be its length. And then if this height right here is C, then to get up here, what I have, this is kind of, I'm going to pull this out and draw it to the side. This has a length of A square root of A squared plus B squared. This has a length of C. If I square this, do Pythagorean theorem, I have A squared plus B squared plus C squared is equal to this, call that D, D squared. So the magnitude of that vector that starts here and ends up there ends up being, the magnitude of A, B, C would be equal to the square root of A squared plus B squared plus C squared. So notice, moving from 2 dimensions to 3 dimensions, it's very similar. We just now have a third value to consider. Okay, so what does it mean for vectors to be equal? They have to be, they have the same direction and magnitude. What does it mean for vectors to be parallel? Parallel vectors, well, if I have a vector like this, I can be parallel if I'm doing something like that. I could even be parallel, I could even be parallel if I do something like this. Okay, so their magnitudes don't have to match, and their directions need to be the same or the opposite. So for what does it mean for vectors to be parallel? They have the same or opposite direction. And so what we'll say is that A is parallel to vector B if, well, maybe even if and only if, A is equal to some scalar k times B as long as k is not 0. Okay, so that means I can multiply vector B times something and get vector A. So say B was the vector, well, say B was vector 1, 2. Well, then if k were equal to 2, then vector A would be equal to 2, 4, and that would be parallel.